Hi friends, today let's talk about the chapter 1 of design data intensive applications. So there are essentially three goals when you design a data intensive application. Reliability and also the scalability and lastly the maintainability. Reliability describes that when you have a request, how reliable is your system to return the expected response. And scalability is basically saying that we have larger load. How will your system handle that? Lastly, maintainability is talking about daily operations, daily deployments, how do you evolve your system? Let's talk about them one by one. So let's start talking about reliability. In order for your system to be reliable, you actually need to reduce faults. So there is a distinction between fault versus failure. The distinction is that fault means that your system usually deviates from its expected behavior, usually because the input is unexpected. But failure, it just means that your whole system shuts down. It stops giving the user the expected response. So failure is more of an issue compared to fault. But here, we're also, when talking about reliability, we talk about reducing fault. And having this mindset that fault is inevitable, the system we want to design is to be fault tolerance. There are three types of faults. We have hardware faults, we have software faults, and we have human faults. The hardware faults, for example, your hard drive might crash. You could have some RAM faults, and there's possibly power outage in your data center. These are inevitable, especially in the modern architecture when you have a cluster of machines. Even though hardware is usually the most reliable component in a data system, but when you have hundreds of thousands of machines, as long as one of them has faults, you actually encounter some kind of uncertainty in your data system. Hardware faults is usually more independent. Like this machine fails, doesn't really mean that machine will fail. The way to deal with hardware faults is to add redundancy, so that one machine fails, the other machine can pick up. Now let's talk about the harder to deal with issues, the software faults. We just talked about hardware faults, more independent, but software faults can be more correlated. Its software faults are usually more fundamental and systematic. It means that with the software faults, when this machine fails, the other machine could also fail. So redundancy is not in the table right now. Concretely, software faults could be like an external dependency has issues, version issues. There may be a bug in the code that was triggered only on occasional unusual inputs. There's no good way to essentially prevent software bugs and software faults. The way to do this is mainly self-discipline. We talk about more tests, also better monitoring. And lastly, we talk about the human faults. This is something like a misconfiguration, and people usually are not that reliable compared to machines. This is pretty common. Similarly, human faults are harder to prevent. So the way to do this is similar as above. We can add more tests and with better monitoring and automation to reduce human faults. Now let's talk about scalability. Scalability means that how your data system handles with increasing load. But what is load? Load means the number of requests that is passed to your system. For example, QPS is a metric to describe load. And let's talk more concretely about what is load, how to describe load. So in addition to the common metrics such as number of requests per second, we can look into a concrete example using Twitter. Twitter mainly have two functions. One is post, the other is homeline. Post means a user can send tweet, and homeline means that user read the tweets from creators that the user follows. The special case of Twitter is that it also needs to consider the fan out, which means the number of users this user follows. Concretely, how they can design the data system, there are two ways. So the first approach is a naive approach. When the homepage request comes in, you find out what is the user ID and find out all the creators that this user follows, and then fetch the tweets of these creators. So this is a naive approach. But as you can imagine, this can be very slow because first of all, the home line request is like 10 times the post requests. So essentially there are just more read requests than write requests. And secondly, it is common that the user follows more creators, and then this will increase latency and increase the system burden. That is why we also have the second approach. So in the second approach, we create a cache. So when user posts a tweet, we will find out whoever followed this creator and then send that tweet to the followers cache. Like for example, this user posts tweet and then these are his or her followers 1, 2, 3, and then you distribute these tweets to the followers corresponding cache so that whenever this user requests home line, we just read the cache instead of doing another SQL run. Given there are less post requests compared to home timeline requests, this one will give less system burden. But you might say, there may be celebrities or people who are super popular, they have hundreds of millions of followers. So in this case, you have to distribute and do this for hundreds of millions of followers. This isn't very realistic. That is why Twitter actually incorporates both approaches. For the celebrities or people who have a lot of followers, they can do approach 1. And for average creators, they do approach 2. This example shows that describing the load is not just number of requests per second, but it's more complicated than that. You have to consider fan out, number of followers per creator in this case. Now let's talk about performance. There are two perspectives. Think about this. When you increase load to maintain the same performance, how much resources do you need to add? And second is that when you increase load, but then you keep the same resources, how much performance degradation are we expecting? So both cases, we need to have a way to describe the performance. Essentially, we divide the data systems into two categories. One is batch processing, the other is online service. Batch processing systems can be Hadoop. Usually, the way to describe Hadoop systems performance is throughput, the volume of read and write at a unit of time. And there's also online service, for example, a web application. So for this kind of service, the response time can be an important performance metrics. Now that we have ways to describe load and describe the performance, we need to think about a way of how to cope with load. So when there's increasing load, how do you scale your data systems? There are mainly two categories of thoughts. First of all, is to scale up, and second is to scale out. Scale up means that you use more powerful machines, and we also call it vertical scale. And scale out means that you use more machines, and we'll also call it horizontal scale. As you can see, scale out is better for the stateless machine. If your machine has state, then scale out will be quite troublesome. A good data system nowadays has both approach. It uses a mixture of vertical and horizontal scaling. Now let's talk about the third goal of designing data-intensive systems, which is maintainability. There are three main categories of maintainability. First of all is operations. So operationability. That means your day-to-day deployment, your CI/CD, your code quality, so all those things, especially how you convert code to deployment to production. For example, you can do some canary tests to ensure your deployment is safe. Some automations on deployment. Second is simplicity. When you have multiple people co-working on the same code base, the logic can be inconsistent, and code can be here and there. Code quality is hard to maintain, and it will just increase the complexity of the system over time. This is fine if you don't touch the code, but as long as you want to debug or something went wrong, it will be very hard to debug. So the solution to making this system more simple is to have good abstractions, good interface. This is not easy and requires periodically refactoring. So again, it's kind of a self-discipline to make sure your system is simple. But simplicity is crucial to debug your system and to make sure that people understand it later on. And next is evolvability. Evolvability means that you have this system, but you want to add on new features. How difficult it is to add new features. What is your iteration speed? Essentially, you want to have a system that allows you to iterate new features fast. How can you do that? First of all, you have to have an easy to understand system to have good abstractions. And second of all, you need to periodically refactor. So all in all, that's the part about maintainability. Although we put it in the last, it's actually pretty important. Most of the people live in a legacy code base. It is crucial to make it easy to operate, simple, and easy to add new features. So to summarize, Chapter 1 talks about 3 goals when you design a data-intensive system. First of all, is reliability. You want to reduce fault and make your system consistent in delivering outputs that user requests. And second of all is scalability. Scalability is how your system can handle increased load. When there's increased load, you can scale up and scale out. Modern systems have a mixture of horizontal and vertical scale. And lastly is maintainability. You want your data system to be easy to operate and be simple enough to debug and easy enough to add new features. That's it. Thank you for watching. See you next time.